Hello everyone, this is Greg Stitt from the University of Florida. In this video, I'm going to be explaining the RTL code that is used in this CCIP MMIO example for the Intel PAC. So in this video, I'm assuming you've already watched the earlier video I posted about how CCIP works and the timing of all the signals on the interface and things like that. So this video assumes you understand how the protocol works, and I'm going to be explaining how you create the RTL code that essentially implements that protocol. And so a completed solution is already provided on the GitHub repository as shown here. But in this video, what I'm going to do is strip out most of that code and write it from scratch and explain everything as I go along, just so that you understand what every line of code does. Before I actually get to the code, first, let's take a look at the directory structure. So if you go inside this hardware directory, there's a bunch of files in here. So first of all, one file you should be familiar with is this file list. So if I open that up, actually I have a Emacs down here. If I open up that file, what this does is specifies a list of files that are needed by the hardware AFU. And so I won't explain exactly why you need this in this video, but I'll have other videos where I show you how to simulate this and how to synthesize this. And the OPE scripts basically need this file list in here in order to work correctly. And so you have to make sure that you list all of your RTL files in this file list.txt or some other file. Otherwise, those simulation scripts and synthesis scripts will not work correctly. So there's one other file you need to be familiar with. So there's this JSON file, the AFU.json. So every AFU create needs to have some basic information specified in here. And I explained this in the earlier video, where this file basically specifies all the characteristics of the AFU that are needed by both hardware and software. So you have a name here. I just generically called it AFU because this doesn't really have a specific purpose other than training. But what is very important is this UUID here. This has to be unique for every AFU that you want to run on the FPGA. So the way that you generate this is if you run UUID gen from the command line, it gives you a long hex number here. You can just copy and paste that into the JSON file and you have a unique identifier for your AFU. So it's very important that you do that. By the way, if at any point you see me run some command from the command line and it doesn't work for you, it likely means that you don't have OPE installed correctly, or you don't have the right environment variables, or you don't have the environment variables configured correctly. So that will be covered with other information. So for all of my videos, I'm assuming you already have OPE installed and you have all your environment variables configured appropriately. So there's a bunch of other information you could change in here. We're going to leave it the same for this example. So we just have a name and we have an identifier. So other than that, we just have a few source files, a few system verilog files here. So the top level file for our AFU is actually specified in the JSON file. It's the CCIP Standard AFU. So let's open that up. And then we make this a little bigger. So if you look at all of the Intel reference examples, they basically use this as a top level, and so I would recommend just sticking with that unless you have a very good reason to change it. I explained all these signals in the earlier video, so I'm not going to do that again, but I just want to take a quick look through here so you know what's going on. In the earlier video, I basically mentioned that the AFU exists within a partial reconfiguration region, and PR regions have to have registered I/O. And so there is this entity or this module right here that basically does all of that for you. So if you just don't change this CCIP standard AFU, it will already register all of the entire interface, so you don't have to worry about it. And then the really kind of important part is down here. I've modified this file so that it essentially instantiates another AFU module that is has a simplified interface compared to this one up here. So you're welcome to use this one directly, but it has features that probably go beyond the majority of AFUs that you would create, and it certainly goes beyond what is needed for these simple training modules. So I've created this AFU module down here just to make things a little bit simpler. So we're going to focus most of our attention to what's inside of this AFU right here. All right, so what I'm going to do is just kind of step through this code line by line, and we are going to implement the CCIP MMIO example. That was the memory mapped communication with registers over CCIP, the Core Cache Interface Protocol. And just to quickly review what that example did from the previous presentation, we memory mapped a single 64-bit register. We mapped it to the address 0020 hex, and then we implemented the code to be able to write to that register from software and read from that register from software. And we also implemented the other basic requirements, the MMIO requirements of any AFU. All right. So the first thing that we probably want to do is come up with the identifier for our AFU, because we're going to need to give the software that information to be able to identify the current AFU that's loaded in the FPGA. So the way we do that is, you could do this in a bunch of different ways. You could just copy and paste the identifier into your RTL code here. But it's better to do it in a way, since the ID is needed by hardware and software. You don't want to run into coherency problems if you modify it in one piece of code but not in the other piece of code. So if you're going to change the ID, you put it in the JSON file, and then when you run the simulation or synthesis scripts, those will generate header files. So up here you see this AFU JSON info.vh. That file gets generated when you run either the simulation or synthesis script, and inside of that file you will see there's a constant called AFU Excel UUID. So what we're going to do is just take that constant and store it into something we call UFID in our code here, and then we have a convenient way of referring to that identifier. All right, next we're just going to create the logic for our register. We'll call that user register. That's what I called it in the slides before, so I'll keep that consistent. There's another thing we have to do. So if you go back and watch the CCIP presentation on MMIO, I mentioned in that presentation that on the receive port of the Core Cache interface, there's the C0 channel that has a header. So basically, we can access that header by basically doing this. The problem is that header by itself is kind of overloaded for different purposes. So we want a header that specifies the information for memory mapped I/O. So that interface by itself does not provide that. And so because it's overloaded for different purposes, we have to essentially cast it to a type that converts those wires into what we expect to see for memory mapped I/O. So basically there's this type here, hopefully I'm remembering this correctly. That I'm just going to create an instance of this type and call it MMIO header. And then what I can do is essentially cast that C0 header port to this type. And now this MMIO signal does actually contain all of the information that we need. So we're going to need to see whether or not, we basically have to see the address of the write and various other things. And without casting to this, we don't have a convenient way of accessing the address signals within this port right here. So now we do, because we have this MMIO header and we can read from that directly. So next what we're going to do is implement the user register and the MMIO write to that register. All right, so we're going to have an always flip-flop block. We're doing that because we want to create a register. It is going to be triggered by a positive clock edge, or alternatively a positive reset edge. So I like to use asynchronous resets generally when I'm working with FPGAs. It depends on the FPGA, but that's generally what I will do. All right, so on reset, what do we want to do? Well, we want to most likely reset our register. We don't have to necessarily do that, but here I'm going to reset it. I'm just going to set it to 0, and the reset. And then after that, we are going to basically specify what happens on the rising clock edge. All right, so on the rising clock edge, we need to check to see whether or not an MMIO write is occurring. So if you go back and watch my previous video where I explain CCIP, basically on the receive port, or on channel 0 of the receive port, there is this MMIO write valid signal. And if that is 1, then we know a write is occurring. So when we are inside of this if statement here, we know that a write is occurring. But we don't know yet where that write is what address corresponds to that write. So at this point, we know software is transferring something into our AFU, but we don't know where yet. So to figure out where it wants to write that data, we have to check the address. And this is why we had to cast the channel 0 header of the receive port into this special type, is so that we can get the address from the MMIO header. So what we can do here is, basically check to see if the address corresponds to the address that we assigned to our user register. That was 0020. If that is the address, then we basically want to assign the data coming in on channel 0. So that's just C0 data. And we can explicitly say 63 down to 0. Although, if I remember correctly, that is a 64-bit. I don't remember if that's 64 bits or not, but it won't hurt if we do 63 down to 0, since we have a 64-bit register. All right, and that's actually everything for the MMIO write. So it's basically just a register where we are only writing to the register when, first of all, the processor is trying to write to the AFU, and the address corresponds to the address that we assign to our register. So if we want to have a different register, we just simply change this address and have another register signal here. All right, so that's simple enough. So now we have to implement the read code. And this is also going to be done with registers, because this is going to use the simplification I talked about in the previous presentation, where we are always going to respond to a read within a single cycle. And we're going to do that by just using a set of registers. So if we just delay the incoming control signals by a cycle by using a register, then the timing works out exactly like we want. So again, we want this to be triggered by the positive edge of the clock or the reset. So if we are resetting the circuit, there's a few things we have to do here that are different than what we did on the MMIO write. So there's basic information on the transmit port that we have to provide that specifies whether or not we're responding to a request. In fact, I'm just going to copy and paste some of this from the solution to save some time. But there's basically these signals here that are responsible for responding to a request. And so on reset, I'm just going to set them all to 0 so that as soon as we reset the circuit, we're not accidentally responding to a request. All right, then otherwise on the rising clock edge. So here we need to do a few things. So the basic way we tell the processor that we're responding to a request is on the channel 2 of the transmit port. There's this MIO read valid signal. And when that is 1, that's basically how we're telling the processor that, okay, we're responding to a read now. You've requested a read and here's the response to it. Except by default, we don't want to, we want to basically say we're not responding to a read because the vast majority of the time, we're not going to be responding to a read. So next we need to check to see if there actually is an incoming read request from the processor. And we do that in a way that's very similar to what we did for a write. So we checked for a write using this code up here. For a read, we basically do the same thing. But we just check the MMIO read valid signal instead of the write valid signal. All right, so if we enter this portion of the code, we know the processor now is requesting a read. So there's a few things we need to do to respond to a read. One is we have to specify the transaction ID that we're responding to. And so the incoming transaction ID is specified as part of this MMIO header that we created earlier. There is a transaction ID signal in that structure. And so we have to respond, we have to specify the transaction ID in our response, which we put on channel 2 of the transmit port. There's this header there, and there's a transaction ID field of that header. And so if we do this one line of code here, this will create a register for the transaction ID that is used for the response, and the input to that register is the incoming transaction ID. So this one line of code is basically delaying the transaction ID in the request by 1 cycle, and that's exactly what we want, because we're always going to respond in 1 cycle, at least in this implementation that we're doing here. We also have to tell the processor or CCIP that we actually are responding. And so you do that with the MMIO read valid signal on channel 2 of the transmit port. Oops. And again, this one line of code will create a register. So it's basically delaying the incoming request by 1 cycle. And then finally, we have to actually provide the data that is being requested. And so the processor provides an address, and we have to look up the corresponding resource based on that address and provide that data back to the processor. So what that means is we need to check to see what address is being requested for the read. So again, we do that the same way we did before. We look in the MMIO header, and in that header, there is an address, and then we just have to kind of go through all the different memory mapped registers that we have. And so for the one that we created, it was mapped to 0020. And so if that happens to be the address, then we want to respond providing the appropriate data on channel 2 of the transmit port. There is a data signal that is responsible for taking the data that is part of the read response. And then we want to provide that, the data we want to put on that port is what we have in our user register. So this one line of code creates a register for this data port. And again, that's exactly what we want, because we want to delay we want to provide that data 1 cycle after the request. And so because this is a register, it will get this data 1 cycle, basically 1 cycle after the read request is noticed by the AFU. And so the data signal here will be aligned with the MMIO read valid response and the transaction ID response. So essentially by using 3 registers, we have all the control we need to respond within a single cycle. All right, so ideally you would be done But for any AFU you create, there is a bunch of other MMIO reads that have to be implemented. So I'm going to copy and paste this because it's not a short amount of code. All right. So for every AFU you create, you have to respond to an MMIO read at address 0 with the information that is shown here. This basically specifies that this is an AFU. It has some information about the AFU. You can probably just copy and paste this for every design that you work with. And then at address 2 and address 4, this is very important because this is where the AFU provides the identifier for itself. So if you remember way up here at the top, we created this AFU ID signal that got this constant that was automatically generated from our JSON file. Well, now down here, we are going to use that to respond to requests for the ID. So this has to be done across 2 different addresses because these MMIO reads, the way we're implementing them is for 64 bits of data. You can do 32-bit reads and 64-bit reads. But for these purposes, the ID has to be provided as part of a 64-bit read. So these addresses you see here are actually for 32-bit words. But since the processor is expecting 64 bits back when it reads this address, we have to implement this the way it's shown here. All right, so when the processor is reading from address 2, that means it is requesting the lower half of the AFU's ID. And so we want to grab bits 63 down to 0. That is the lower half because the ID is 128 bits. When the processor reads from address 4, then we want to return the upper half of the identifier. And then addresses 6 and 8, these are basically reserved spots that you shouldn't do anything with. And so here I just have them set to 0. And then finally, there's something else you don't have to necessarily do this. But what you could do is if the processor requests an address that isn't mapped to anything, you could essentially do something very similar to this, where you return 0 or whatever value you want to return. It doesn't really matter. You might have a purpose for that, but I personally would just return 0. And that is it for the RTL code. So in another video, I will show you the corresponding software code. So I'll show you how to write C++ code using the OPE API, or at least a C++ wrapper that uses the OPE API that will communicate with this RTL AFU that we just created. And then in another video, I will show you how to simulate this using Intel's ASE environment. And then I will show you how to synthesize this. And finally, how to actually execute it on the FPGA on the dev cloud once you've synthesized it.